In our everyday world, we are used to predicting where things are. A car moves on a road. A planet moves around the sun. A ball follows a predictable path. But when we enter the quantum world, things begin to change. So here's the question. Can we predict exactly where an electron is? In classical physics, an electron was imagined like a tiny planet orbiting a nucleus. At any instant its exact position could be known. But quantum mechanics tells a completely different story. Instead of existing at one exact location, the electron behaves more like a spread-out probability cloud. We can no longer say, the electron is exactly here. Instead, we can only calculate the probability of finding it in a particular region of space. Can we predict exactly where an electron is? The electron behaves like a probability cloud. This is one of the biggest shifts in modern physics. The electron is not simply a tiny ball moving around. Its behavior is governed by probabilities, waves, and uncertainty. And this raises another important question. How do we mathematically describe something that behaves like a probability cloud? The answer comes from one of the most important equations in quantum mechanics, the Schrödinger Equation. This equation describes how a quantum system evolves with time. Let's begin with a single electron. At first, it appears localized, almost like a tiny particle. But once energy interacts with the system, oscillation emerges. Particle transforms into wave. As the wave spreads further, it forms what we call a probability distribution. This probability is mathematically represented by psi squared, the square of the wave function magnitude. This equation governs everything you just saw. And all of this behavior, the oscillations, the wave formation, the spreading probability. In the quantum world, certainty begins to disappear. At the heart of this strange reality lies one equation, Schrödinger's wave equation. An equation that doesn't describe particles as tiny balls, but as waves of possibility. Imagine dropping a ball into calm water. The moment it touches the surface, ripples spread outward in every direction. A disturbance becomes a wave. In classical physics, we expect objects to have exact positions. We know where the ball is, where it's going, and where it will land. But quantum particles behave differently. An electron doesn't move like a solid object. Instead, it spreads through space like a wave. This wave evolves continuously over time, not as certainty, but as probability. To describe this strange behavior, quantum mechanics uses complex waves. One part oscillates like cosine, another like sine. Together, they form a complex wave function, a rotating mathematical wave, carrying all possible information about the particle. The real and imaginary parts continuously exchange energy, creating motion that can only truly exist in quantum mechanics. From one perspective, it looks like two separate oscillations. But from another, we discover something deeper, a rotating quantum helix. But the wave itself is not directly observable. What we actually measure is the probability density, the square of the wave function. Where the wave is compressed, the probability becomes higher. Where it spreads out, the particle becomes less likely to be found. Now, let's understand what this equation truly means. I is the imaginary number used in quantum mathematics. H bar is the reduced Planck's constant, the quantum scale constant. Del psi by del t means the change in the wave function with time. H hat Hamiltonian operator is the total energy acting on the wave function. First term represents kinetic energy and V represents potential energy. Psi, wave function describing the quantum state of a particle. Schrödinger's equation does not tell us exactly where a particle is. Instead, it tells us the probability of where it could be. And from this single equation, modern quantum mechanics was born.